So, Jai Hind everyone. My name is Ritesh Sharma. I am from Ajay Kumar Gar Engineering College, Ghaziabad, and I am teaching subject of the fundamental of electrical engineering in the first year. The subject code is BEE 101. So, today's topics is basically based on the unit number 3, and the topic is phasor diagram of single phase transformer. So, in our previous lecture, we discussed about some basic introduction about the transformer operation on load and no load, and then today I will discuss the phasor diagram of single phase transformer. So, phasor diagram of single phase transformer, it means it is a actual transformer, means it is not a ideal transformer. So, in actual transformer, this is the circuit diagram of the actual transformer, in which we have to consider the resistance of the primary and the secondary winding and the leakage reactance of the primary and the secondary winding. So, as you can see that R1 and R2 are the resistances of primary and the secondary winding. X1, X2 are the leakage reactance of the primary and the secondary winding. So, if you combine them, it is the impedance of the primary winding will be Z1 and the impedance of the secondary winding will be the Z2. So, applied voltage is V1. We have applied the simple single phase supply, that is the voltage V1, and the voltage induced in the primary and the secondary winding will be E1 and E2 respectively. So, here the load is taken at, suppose this is my load and it is Z, and the load could be your resistive load, inductive load, or it may be also capacitive load. So, depending upon the load, there will be some power factor of the transformer will be there. So, here the two parameters are called, this is the no load current, is this, and this is the primary current, and you can see that the primary current from here, the primary current I1 must be equal to the no load current plus this is I2 dash, which is the load component of the primary current. So, let us focus on the phasor diagram of this single phase transformer or actual transformer. Okay. So, these are the some parameters which I just told you. This is the R1 is the primary resistance, R2 is the secondary resistance, I0 is the no load current, I mu and IW which is mentioned here. This is the IW is also called working component or it is also core loss component. And similarly, this I mu is the magnetizing component of the no load current. So, these are the parameters, these are the some nomenclature of the. Now, let us draw the phasor diagram. So, to draw the phasor diagram, first of all, phasor diagram of this transformer, first of all, we have to write the input and the load equation of the load voltage equation of the transformer. Okay. So, first of all, let us write the input equation. So, we applied the voltage V1 here. We applied the voltage V1 and the voltage induced in the primary is E1. So, you can say that if you apply the KVL in the primary circuit, we can write, we can say that this V1 is equal to E1 plus the voltage drop in this particular parameters, resistance and leakage reactance. And since the current is I1 flowing in that, so it will be equal to I1 R1 plus JX1. Simple. And these are the phasors. Okay. So, it's a phasor sum is equal to this V1 is equal to E1 plus I1 into R1 plus JX1. But here one thing is that this voltage V1 is a applied voltage and E1 is the induced EMF. So induced EMF, because of the Lenz's law, we know that its polarity will be reverse, or it will be of minus sign. Okay, so this is the first equation as far as the primary side of the transformer is concerned. Now next, write the secondary side equation. The secondary, again, the voltage, this is the E2 is the voltage across this winding E2, and V2 is the terminal voltage or the load voltage. So E2 must be equal to, here, this E2 must be equal to V2 plus current is I2 into R2 plus JX2. So this is the voltage equation of the secondary side or load side, you can say. So unless you understand this equation, it is very difficult for us to draw the phasor diagram. So first we need to understand these two, primary side and the secondary side equation of the transformer. So next, for when we draw the phasor diagram, we have to assume that the load on a transformer, the load, it could be your inductive or capacitive or pure resistive. So depending upon that, the load is inductive, capacitive or resistive, the power factor of the transformer has to be decided. Okay, so in case of inductive load, the current will lag the voltage, the current I2 will lag the voltage V2 by some angle, and in case of capacitive, current I2 will lead the voltage by particular angle, and then in case of purely resistive circuit load, the current and voltage has the same phase, okay, along the same phase. So first we assume that first we write that for inductive load, the current I2 will lag the voltage by a certain angle. So first of all, we draw the phasor of transformer. Suppose this is the first flux, phi is taken as a reference, because we know that the phi is equal to phi m sine omega t. This is the flux, and we assume that the phase of the flux is 0, or we take as a reference actually. Okay, and then we will take the induced EMF E1 and E2, and E1 and E2, the voltage induced in the E1 and E2 will lag the flux by angle 90 degree, as we have seen when we derive the equation for the E1 and E2. So this E1 and E2 will be lagged by angle pi by 2. Suppose this is my E1. E1 is this angle is pi by 2, 90 degree. 90 degree is the angle. So we know that the voltage induced in the winding, whether it is the primary winding or the secondary winding, will lag the flux by 90 degree. Now another thing is that we have assumed that the load is inductive, so current will lag the voltage by V2 by some angle phi. So suppose that V2 is let us take the another angle. This is my V2. V2 is nothing but a phasor of load voltage or terminal voltage, and since it is an inductive load, the current I2 will lag this voltage by some angle. Suppose the angle is phi 2, because the cell load side we assume that it is phi 2. So I2 will be around, this is our I2, and the angle is phi 2. Okay, so you can say that the current is lag the voltage by angle phi 2. Now again, when we see this secondary side equation, this E2 is equal to V2 plus I2 R2 plus J I2 into X2. So this I2 into R2 is the, and this J I2 into X2, and this V2. So this I2 R2 is the ohmic drop that is in the phase with the current, and this I2 X2 is a drop which is a 90 degree ahead of this current actually. Okay, so if we draw this phasor of this, so we just add I2 R2 in phase with current I2. So this is the I2. So in the phase of I2, you can just extend this in the phase along this I2. This will be I2 R2, and the I2 X2 will be 90 degree lead by this. So 90 degree like this. See something here, and if you extend this part, it will be your E2. This is my I2 X2 J. So we can see that our E2 is equal to V2 plus I2 R2 plus J I2 into X2. So this is the phasor diagram as far as the load side is concerned. You can also, if you connect this this, and this will be your I2 Z2. Okay, and if you can see that, this triangle, the shaded triangle is nothing but it is the voltage triangle. It is a voltage triangle, because in the obviously this side is having the inductive nature, or the coil is there, resistance is there, leakage reactance. So this is a I2 Z2, X2 I2 X2, and I2 R2. So this is a voltage triangle. So this is the secondary side of the load side. Now next is to draw the secondary side voltage equation. The phasor of secondary side, first of all we have to assume that the load current is there, because the primary current, the load current is also there, and we know that this I1 must be equal to I0 load component. We have seen that in the previous lecture. So the primary current is equal to, when at load, when the load is connected, the primary current is equal to load, no load current, and the load component of the primary current. So this is the primary current. Now I0, we all know that the I0 is the no load current, and this nature of no load current is something like this is the I0. So I0, we know that this I0 having the voltage, the angle between the voltage and I0 is almost 80 degree to 85 degree. Okay, and is I0 having the two component, we know that the core loss component, and that is IC and I magnetizing component. So here we will drawing only the I0 only. This IV1 is equal to minus of E1. So if E1 is this, so minus of E1 is just opposite of this, and it could be here, just opposite of this is like this, just like this is our E minus of E1. You can mark minus because it's opposite polarity of this. So V1 is equal to minus of E1 plus this. Again, we have to incorporate this drops I1 R1 and I1 into X1. But it is along the I1. So first we have to find the I1, the primary current of the transformer. And we know that the primary current is nothing but it is a, so I0 is already there, then I2 dash is, I2 is this, and I2 dash is opposite of I2 because it's the current which is flowing opposite to that of I2. So I2 will be the same color. Same color is this. This is I2 dash. So I2 dash and I0. Now take the phasor sum of I2 dash and I0. And come and join this. This is I1. So I1 is the phasor of I1 can be drawn like this. Take the I0 current, no load current, and I2 dash, which is opposite to that of I2. Okay. So now let us draw the phasor of I1 into X1 plus I1 into R1 and then I1 into X1. So I1 R1 always will be in the phase of I1 current I1. So take the I1 is this. So current I1, you can just draw this along the I1 R1. And to draw it, we have to let us erase this part because otherwise it won't be possible for us. Next is the I1 R1 and then I1 X1. So I1 X1 J 90 degree lead by this. So 90 degree, this will be around this. So it's 90 degree will be like this. Something like this. So J I1 X1. I hope you can see that part. So J I1 into X1. And now this is a V1, which if we join the initial part and the final one, we will calculate the voltage V1. So for that we can take from, if it is 0, suppose. So if we can join this, this is the V1, the phasor of V1. This is minus E1, I1 R1, J I1 X1, and now this is the phasor of inductive load. So this is basically the phasor diagram for inductive load. For inductive load. Okay. So where the voltage and current the current lag the voltage by some amount, some phasor, some phase, suppose phi 2 is there. It depends upon the load actually. How your load is this, power factor actually. So next we can find the phasor diagram for the purely resistive load. Suppose if we take the purely resistive load, in case of pure resistive load, for pure resistive load, for pure resistive load, for pure resistive load. For pure resistive load, we know that the voltage and current will be in the same field, same phase. So from here, if this is the phasor for the inductive load, if we try to draw it for the pure resistive load, take the current for flux as a reference again, that is phi E1 and E2. This is our E1, voltage induced in the primary winding. Again, the E2 will be in the same, the E2 will be in the same phase. Suppose this is E2, and if you take the voltage V2, and V2 and I2 will be in the same phase. So take the current I2 in the same phase, I2. This is our I2. So V2 and I2 having the same phase, no power factor is almost unity because cos 0 degree is a 1 unity. Now from here we can, from the same equations, these equations, we can apply these equations. So first E2 will be equal to V2 plus I2 into R2, because if we write the equation for that, the V2 is equal to, E2 is equal to V2 plus, so E2 must be equal to V2 plus I2 into R2. So this I2 R2 drop will be in the phase of I2, and the I2 is in the phase with the voltage. So this can be extended as like this, I2 R2, and then I2 X2, which is in the 90 degree. This is JI2 X2, and if you extend this, part, this is called a E2. Now this is our E2. So phasor of E2 is drawn like this. Again, you can say that this part, if you V2 plus I2 R2, this is called I2 Z2 impedance taken, and this is our voltage triangle of the secondary side. In the previous question, when we drawing this inductive load, this is the voltage triangle. Again, you can draw the voltage triangle for the primary side by simply connecting this, and this is your I1 Z1. So this was the part of this. Similarly, if you drawing this for the primary side, so flux will be like this. This is the no load current. This is I1 E1 opposite, minus of E1, and then I2, the opposite of I2 is I2 dash, and I2 dash and I0 will be in the same phase. The phasor sum of I2 dash and I0 is I1, that is this and this. So this must be your I1. So equation of the current will, this voltage will remain same. These equations will remain same. We have to apply the same equation actually. So I1 is this. Now V1 will be equal to, as V1 is equal to minus E1 plus this drop, the drop in the primary winding. So this I1, we can take the different color, and this is your I1 Z1. So here you can see that this is the phasor diagram for pure resistive load. So in pure resistive load, the voltage and current of the load side will be in the same phase. This is the only difference only to draw the phasor diagram actually. This is not actually a perfect line, but it is a straight line. So this is the I1 Z1. Similarly, you can draw it for the capacitive load. for capacitive load, where the current will lead the voltage by angle. Like for example, for capacitive load, I'm just trying a few steps. Like this is phi, this is the E1. So if this is your V2, so for capacitive load, this must be your I2. The angle between this phi 2, it depends the how the current, the power factor of the load actually. That is the angle between the voltage and current, and then further steps you can draw in a similar way. Okay. The only difference is that here the current will lag the voltage by angle phi 2. So this is basically about the phasor diagram of you can see that if you start with the beginning, the first of all we have to understand the equivalent circuit, the actual transformer. So this is the equivalent circuit of the actual transformer having some the primary voltage resistance, secondary resistance, leakage reactance we have to consider, and the no load current is also there. And then depending upon the load, whether it is inductive, capacitive or resistive, we can draw the phasor of transformer. So these are some steps that you can follow to understand how to draw the phasor diagram. So I hope this lecture is very benefit for you. Thank you so much.